Hello! So, at the end of the last video, I left off by finding the instantaneous rate of change of a function, and I was just about to tell you exactly what that meant. Now, let's go back to the function we had. I think we had f of x, our function, is equal to x squared. So we had, 1, let's say, it's 2, and this is 1, 2, 3, 4. It's not that important. Let's just get a reasonable sense of things. Alright, so there's our function, and this goes back in the other direction, like this. We don't care about that direction right now. And we found, if you haven't seen my other video on an introduction to derivatives, watch that the derivative of f of x, which I'm going to introduce now with some notation, f prime of x was equal to 2 times x. And what does that mean? That means we found the slope. This means the slope. This can also be, this here is also equal to, some more notation, df over dx. And this, intuitively speaking, d means kind of an infinitesimal point, or in this case, change, infinitesimal change, that's what it means. And so, this is basically delta y over delta x. This can also be equal to, written as dy over dx. And it's basically just the rate of change, delta y over delta x, but infinitesimally. So in 1 point. Now, what does this mean? So, that means if we choose some point along this graph, let's say point 1, we slide that into the equation, and we find that our slope at that point, and we write it as f prime, just as if we were doing a function, which is what it is, of 1 is equal to, I'll plug it in, 2 times 1 is 2. Similarly, at the point 2, 4, and we only really care about the x value because we have it as a function of x, f prime of 2 is equal to, well, let's say 2 times 2, that's 4. And, that just continues on. We can plug in any point, even negative points, and find the negative slope. Alright, so that's really cool, but why? And I will get to that in later videos. On a short note, it's very useful in determining values, maximum values, minimum values, and a lot in physics. Now then, so we know basically an understanding of how to take a derivative and what it means, but we're still not that good at taking them. So I'm going to introduce you to some other forms of derivative taking and how you can use them to your best. But first, I need to introduce you to some simple rules. You could come over here. And these can be proven. I'm not going to prove them here. For one, I'm going to write like this from now on. dx of the function, in brackets, natural log of x, so that's the power that e goes to get to x, is equal to 1 over x. Right? That can be proven. Not in this video, but perhaps later on. Another. The derivative with respect to x, you can say, another fancy terminology, there are a whole bunch of them, and you kind of need to know all of them because they're interchanged a lot, of cosine of x, if x were an angle, it's the ratio of the adjacent side to the hypotenuse, is equal to the negative sine x. Well, that's neat. And sort of similarly, the derivative with respect to x of sine x, x being an angle where sine is the ratio of the adjacent side to the hypotenuse. I'm not doing a trigonometric lesson here, so I'll have more videos on that later, is equal to cosine of x, not negative, which is similarly fascinating. Nope, not negative. Just said not negative. Alright, so these are core, very core derivatives, and they're used a lot. Now, here's another core one, but it's a little bit specialer. The derivative with respect to x of e, the base of the natural log, or natural logarithm, to the x is equal to, fantastically, e to the x. It doesn't care what you do to it, it's just e to the x. It can't go anywhere. And that's very useful and is used a lot as well. So these are important things to know for the future. Now, how about some methods of taking derivatives? And you might want to come a little closer. First, we have what's simple called the power rule. I'm going to write out here. Power rule. Now, this means that, let's say we have x to some power. X. Well, if we're taking the derivative, because that's really what we care about, of x to some power, we take that power, turn it into a coefficient, and then slightly decrement the exponent of our new value, or in this case, a variable, depending. And that would be equal to, like we just said, n times x to the n minus 1 power. And an example, let's use red again. X squared, like we did before using the other method, we found a derivative of, and that derivative was equal to, let's see, 2x. What's that? 2 times x, n times x, to that power, but subtracted by 1, to the first. And yes, that's what it was. 2 times x to the first power. It's just 2x. Where 2 is our n. Right, perfect. That one's easy. It can be used for various other circumstances where you can have, let's give another example. And this also touches on another important rule of derivatives. X squared plus 2x minus 3. We have a quadratic here. And of course, you know, there are ways we could find solutions and things, but that's not really what we care about. We care that using a derivative, we can split these up into groups. We can take the derivative of this one plus the derivative of this one plus the derivative of this one. And that's great. So the derivative of this one first, the derivative of x squared is 2x. The derivative of 2x. Now, 2x is 2 times x to the first power. This is going to touch on another rule, which means that if we have a coefficient here, this can be taken out of the derivative. So this all is the derivative with respect to x of x squared plus, right, because now it's separate, plus, we can take 2 out. 2 times the derivative with respect to x, and derivatives This is really an operator and it can't really be used algebraically, although it is sometimes manipulated that way in integral calculus, of just x minus the derivative with respect to 3. And we can find that that is all equal to derivative of x squared, 2x, plus 2 times the derivative of x. So that's x to the first. So that's 1 times x to the 1 minus 1, which is 0. So 1 times x to the 0th is 1 times 1 is 1. Plus 1. The derivative of x is 1. Right? Because if we have an equation, x, right, this makes sense. If we have an equation y equals x, the slope is 1. That's the coefficient on x. That's what we learned in linear algebra. And now, the derivative with respect to x of 3, well, that's the same as 3 times x to the 0th. 0 gets multiplied to it all. And so, in the end, it doesn't matter. It's just 0. So we can take that out. They don't matter, right? This is like a y-intercept. It doesn't influence the slope, just where the graph is. So this, by the power rule, is the derivative of this quadratic. Now, next rule. This may become a slightly long video because of the many rules. Next rule that I'm going to talk about, and I might not have time to get to them all, is the chain rule. And I'm going to talk about this one a little bit more in the next video, as I won't have time to explain it all in this video. The chain rule is what you use if you have something like, and I'm going to pull out the ones that we learned over here, if we have something like the natural log of the cosine of x, which is basically a function of a function, right? F of g of x. How do we evaluate this? This isn't just 1 over cosine of x, because that would be with respect to the cosine of x. We're treating cosine of x like x. That's not the answer. Now, what the chain rule tells us is that the derivative of something like, I'm going to use this color again, f of g, again this is just generalizable, of x is equal to work out my markers, the derivative with respect to g of x of, or you could, the notation's a little bit, dgx, or dg, or df dg, however you want to write it. But I'm going to write it d over dgx of f of g of x. Alright? Or, yeah. Times, and I'm running out of space here, times the derivative with respect to x of g of x. And you might not be able to see very well. But we take the derivative of the outer one as if g of x is x. We treat g of x like x using our other rules from before, like the power rule, or the rules that we learned over here. And then we multiply that times the inner function with respect to x itself. And I'm going to give one example, and then I'll have to wrap it up. So, right, we already have an example right here. So as we learned, this is the derivative of this with respect to the inner function. So we basically treat this as x temporarily, right? So this is, as we learned, the derivative of the natural log of x is 1 over x. But our x is not really x, it's a cosine of x. We're treating this as if it's our x. And then we multiply this times this inner function with respect to x. We learned that too, it's negative sine of x. Right? And this can be evaluated easily, right? This is negative sine of x over cosine of x is equal to the negative tangent of x, or if x is an angle, the ratio of the opposite side to the adjacent one. Did I make any mistakes? Let me see. Nope. This is our derivative by the chain rule. I'll go over this a little bit more in future videos to come, as well as two more rules, the power rule and the quotient rule, which is really just the same thing as a power rule.